Hello everyone, I'm back with another video of the Digital Signal Processing Laboratory. This is the DSP lab experiment number 5. It is a study of application of fast Fourier transform for the analysis of signals. My name is Shobhit Sahu and my roll number is 17EC01037. The aim of the experiment is to compute the pulse rate for the given PPG data using the fast Fourier transform FFT algorithm. Second part is to extract the respiration information from a mixed signal containing PPG signal and respiration signal both on the Arduino as well as the MATLAB platform using FFT and inverse FFT operations respectively. Next is the fast Fourier transform FFT. It is an efficient version algorithm used to implement discrete Fourier transform DFT. This method uses the divide and conquer technique, which brings down the computation complexity to order of n log n from order of n square. As in case of endpoint DFT, there are two types of FFT algorithms: decimation in time FFT, that is also known as DIT FFT, decimation in frequency FFT, also known as DIF FFT. Here we'll use DIT FFT, where the n-point time sequence x of n is split into even numbered g of n and odd numbered h of n sequence respectively, such that g of k and h of k are the DFT of g of n and h of n. Each of g of k and h of k are again divided into two parts again, and same thing is repeated until we reach the 2-point DFT. FFT can only be performed if n is of the form 2 to the power m and m is a positive integer. The lab assignment. First is to compute the pulse rate for the PPG signal using the FFT algorithm for a given signal of duration 3 seconds. The PPG signal has a sampling frequency is equal to 25 Hz. So what we use is we bring in #include Arduino FFT.h, the FFT library. $x75 is the 75 sample space. The next value next 2 to the power the next value nearest to 75 higher than it, which is of the form 2 to the power m, is 128. Then we set the fs at 25. Double SM samples, V real, V imaginary, X FFT. So V real is to store the real component, imaginary V IMAG is to store the imaginary component, and XFFT is to store the FFT values. What do we do? Begin is with void setup serial.begin 9600. Then first we perform a zero padding. After performation of zero padding, we go to the moving average. So in the moving average, we conduct the moving average filter for 15 window length of 15 for samples and X of SM. For for int I equal to 0, I less than samples, I plus plus, V real of I is equal to SMI, and V imaginary, and we keep the imaginary part of all the values as 0. Then we use the code, that is the current code in the library itself, the functions and or the methods that are already predefined. FFT.windowing, V real samples, FFT win type hamming, FFT forward. Then we do the compute function that computes the V real and V imaginary values, taking the input from the samples and FFT forward. Pulse rate estimation. Now double max is max I location and pulse rate. Max I location is first initiated to 0 and max I is equal to XFFT 0. For int I equal to 1, I less than samples by 2, I plus plus, we find the location where maximum value of FFT is reached and we store the location in maxi LOC, and XFFTI is stored in maxi. Now maxi location is equal to maxi location into fs by samples. That gives us that follows the value k into fs by n to get the pitch frequency, and then the pulse rate is given as maxi location into 60, and then we print it out. So this is the spectrum magnitude for the magnitude response of the computed FFT, and here we can clearly see that the pulse rate using the FFT is 70.31 that has been calculated by us. This is the proper FFT spectrum plot for the magnitude response, and we see that there are two maximas, one over here and one over here. This is the first maxima that is taken into consideration, and no further maximas are taken. This is the first maxima, that is the highest value. This k value is taken, that is the max I location. That max I location into fs by n gives us the pitch frequency, and multiplied by 60 gives us the beats per minute. This is the MATLAB code. Basically this is the same thing, but in this case both the FFT and IFFT have been used using library functions instead of proper numerical methodologies. And here it has we have managed to extract the respiratory information. My 51 is equal to 0. From my 5020 to 1, we have managed to reduce it everything to 0. X residential is equal to x result is equal to I50 my FFT comma I. Maximum value is taken out, and then display rate, that is the respiratory rate, that is should be equal to location minus 1 into 25 into 60 by I. That is accordingly to which we are doing the plots. So these are going to be the plots. This is the given signal that has been provided to us in the lab itself. This is the magnitude response of the frequency spectrum, and then this is going to be the frequency spectrum of the obtained respiratory signal. And then here we've calculated respiratory rate, that is breaths per minute is equal to 16. On performing inverse Fourier like inverse FFT, we have found the respiratory signal only over here. This whole thing is a MATLAB code simulation file. Then this is the Arduino code to extract the respiration or the respiratory data. FFT.compute, here we did FFT.compute. My FFT is equal to new double samples, is a new array that we created, and then magnitudes are filled into it with a window of 100. Moving average filter is applied, and then the my50 values are printed. And accordingly to this is the same procedure that we have followed in the MATLAB code itself, this part. And that is how we've got the respiratory value. The range of the respiratory frequency has been clearly given as 0.05 Hz to 0.5 Hz, and the range of PPG frequency has been given as 0.5 Hz to 5 Hz. So when we clearly see that the values have been distinguishingly changed, this is the whole block, that everything has been done over here. And this is the extracted PPG signal that we have obtained from that, removing the respiratory signal, because the input signal was a combination of both PPG and respiratory signal. Our job was to extract the PPG and respiratory signal in different graphs and to display them. This is the extracted respiratory signal that we have found out with the help of Arduino code, and that is how we have approached this question, and that should be the end of it. Thank you for listening. We'll have another lab in the next week, and the video will be uploaded shortly. Thank you.